Does it really help us remember all the trigonometric formulae and identities we have seen so far? Yes, it does. It's a simple hexagon which looks like this. All we need to do is join all the opposite vertices, and that gives us 3 diagonals. We write the number 1 in the center. It's still difficult to believe that one hexagon can lead us to so many formulae. To know the formulae, we give the 6 function names to each of the 6 vertices. But there is a particular way in which we need to write it. We start writing from this vertex, go around the hexagon and end at this one. It's simple. We just draw a hexagon, join its opposite vertices and write a 1 in the center. Now let's see how we write the 6 functions at the 6 vertices. We just need to remember one formula which we have already seen. Tan is equal to sine by cos. We have used this formula like a zillion times now. Tan is equal to sine by cos. We start at this vertex and write tan, sine, cos in the clockwise direction. Tan, sine, cos. Now 3 functions and 3 vertices remain. We write cot opposite to tan. Remember, cotangent opposite to tangent. What remains is cosec and sec. If we draw a vertical line through the center of the hexagon, we will have 3 vertices on the left and 3 on the right. So to remember what's written on this vertex, just remember that we have all functions starting with c on the right side. So we write a cosec here, and what remains is sec. That's all you need to remember about how the superhex has to be drawn. 3 diagonals joining the opposite vertices, the number 1 in the center, and the 6 functions at the vertices. So let's draw the superhex on a new page. A hexagon with 3 diagonals joining the opposite vertices, the number 1 at the center, tan is equal to sine by cos, cot opposite to tan, cosec here since all c's are on the right, and what remains is sec. Are you ready? You're going to learn a whole set of trigonometric formulae. This video is fun but also very long, as we will be covering most of the trigonometric formulae we have studied before. To understand the first set of formulae, let's try going around the hexagon in the clockwise fashion. We go like this. This tells us that tan theta equals sine theta by cos theta. Well, that's how we started making our hexagon. Now let's see the next 3 functions in clockwise direction. These 3. This tells us that sine theta equals cos theta by cot theta. The first one equals the second one by the third one. Take the next 3 functions clockwise. First equals second by third. Hence, cos theta equals cot theta by cosec theta. And if we take the next 3 functions, we can say that cot theta equals cosec theta by sec theta. And we will get 2 more formulae if we go clockwise. Cosec is equal to sec by tan, and sec is equal to tan by sine. Wasn't that simple? 1 hexagon and 6 formulae without any effort. Great, but what if you forget that you had to go clockwise and you go anti-clockwise instead? Let's say you started like this, in the anti-clockwise direction. Don't worry, the pattern still holds true. First will equal second by third. Tan theta equals sec theta by cosec theta. First equals second by third. If we take these 3 functions anti-clockwise, we can write sine theta equals tan theta by sec theta. If these 3, then cos theta equals sine theta by tan theta, and the list goes on. Whether you go anti-clockwise or clockwise, first will always equal second by third. We can easily get 3 more here. 1 simple hexagon and 12 formulae. Is that all? No, there's more. Let's draw the superhex on a new page to understand what else there is. We draw the superhex and write a 1 in the center. Tan is equal to sine by cos. Cot opposite to tan. As we have all c's on the right, we write a cosec here, and what remains is sec. In the previous set of formulae, we did not use the 1 which was written in the center. Let's see why it is placed like this. If we multiply the functions at the opposite vertices, we get a 1. This multiplied by this equals 1. Sin theta multiplied by cosec theta equals 1. This multiplied by this also gives us 1. Cos theta multiplied by sec theta equals 1. And this multiplied by this also equals 1. Tan theta multiplied by cot theta equals 1. So when functions at diagonally opposite vertices are multiplied, we get a 1. Wait, there's more.